Yes, so good afternoon, ladies and gentlemen. We had already 2 very exciting days of workshop on tandem technologies. We've seen that you have various ways of doing tandem devices. And this afternoon, we have the chance to have an absolutely amazing panels with many people who are doing key contribution to these fields, with 2 industry and 2 representatives of research center being present. So I'm sure we're gonna have a very fruitful and interesting discussion on the topic of which technology is the most promising, and of course, what are the challenging and the possibilities of these technologies also to become product and to enter the market quite quickly. So instead of presenting the member of the panel myself, I will directly ask the various member, and I will give the name of the person who has to speak, to present themselves, where they come from, what they do, and what are their view on promising tandem technology and why they think that the topic on which they work is hopefully promising. So following my screen, I will start directly with Thomas.
Hi, everyone. So I am the CTO and one of 6 co-founders at Swift Solar, which is a company that is specifically looking to commercialize all perovskite tandems, so perovskite front cell, perovskite back cell. And that came out of work that several of the founding team did during our academic careers as PhDs and postdocs at Stanford and MIT, and then after that at NREL. And we're choosing to pursue this technology specifically because we are excited by the unique traits of the all thin film tandem technology. So for example, you could do lightweight and flexible products, which potentially lets us not compete with silicon at an early stage. And that's kind of where we position ourselves, try to do things that silicon cannot do.
Okay, thank you very much. So while I'm just here, before I give the word to the others, I would invite the audience to ask questions in the chat and also to, let's say, vote for questions if you find that the questions are very relevant. So you can put a small thumb on your screen, and if I see that the question gets a lot of attention, then for sure I will try to put this question on the table. So let's continue with Frank.
Yes, hello everyone. Thank you, Christoph. So I'm Frank Dimroth. I'm with the Fraunhofer Institute for Solar Energy Systems in Freiburg in the south of Germany for now more than 23 years. And we work on a tandem technology that kind of is not represented too much in this overall meeting. This is the 3-5 semiconductors, but in fact, I think probably the oldest tandem technology that is around. As you all know, of course, we are at the very top of the efficiency table with the best devices. Adel Tamboli has just been giving a nice talk in the previous session. And we also start looking very much into this 3-5 silicon combination. You see actually a picture, nice picture behind me, which is our most recent triple junction cell directly grown or wafer bonded on silicon. So we can do all of these nice things. And of course, commercially, our main market has been space applications so far. Most of the telecommunication satellites are using our technologies on germanium in that case. And of course, the future that we always try to look for is concentrating photovoltaics, because it's not that cheap to make our solar cells. That's maybe our biggest problem with the market. But we're trying to get better, and we are trying to implement a 3-5 thin film on silicon. So let's see what we can do.
Okay, excellent. Thank you. Now, Chris Case.
Hi there. Thanks, Christoph. So I'm Chris Case. I'm the Chief Technology Officer at Oxford PV, and we're a 2010 spin-out of the University of Oxford, and we're exclusively focused on commercializing perovskites. Our first product is a perovskite on silicon solar cell, and it's actually going to go into volume manufacturing next year in Germany. It's our so-called silicon on steroids, with a first target to go into residential rooftop modules. And so, just a reminder, we're facing a climate crisis, and I get to use that word crisis now. It's been endorsed instead of climate change. And if there's a 50% target for renewables by 2050, that means about 14 terawatts worth of new PV. But because the solar cell is a small part of a solar system, further reductions in the cost of that solar cell don't actually have much of an impact on the cost of the energy from that solar system. So that drove us to look at the only other viable option, of course, is to raise the efficiency, and that leads one obviously to the multi-junction solar cell. So we chose the path to build a two-terminal silicon perovskite tandem because we believed it represented the fastest way to introduce this new thin film material into the marketplace, despite the additional challenges of two-terminal integration. And if you heard Mike McGee's talk yesterday, I think it was yesterday, with the challenges of laser stringing and interconnection, you'd be warned how difficult it is to scale thin film solar. You know, a silicon solar cell has, you know, maybe 250 square centimeters of area. So that's not that big a challenge to scale from a research device, whereas a big thin film solar panel could be 7,000 square centimeters. It's a far bigger challenge. And it's one of the reasons it takes so long to scale and commercialize thin film technologies. And we completely sidestepped that scaling challenge by limiting it to a single device on one solar cell. And we have also thought, recognizing that the market was 95% silicon, and that thin film has never managed to gain more than a few percent of the remaining market share in any of the technologies, that to compete directly with silicon was a mistake. And so in this case, we're actually enhancing silicon. So we're addressing the market that already exists. And by using this same approach of a silicon solar cell, kind of a plug and play approach, it allows very direct and easy integration into the existing module technologies. And, you know, if you look and say, well, it's always hard to introduce new technologies into solar, and I'm sure we're going to get questions about, you know, the various challenges. Look at how fast PERC solar cells replaced aluminum BSF, because they were viewed as an upgrade. And we like to view this kind of solar cell as an upgrade to conventional silicon. So that's all.
Okay, thank you, Chris. Now we switch to our last panelist, Michael.
Yeah, hello everybody. Thank you for inviting me to this panel discussion. Thank you, Christoph. So my name is Michael Powalla. I am a member of the board of the Center for Solar Energy and Hydrogen Research in Stuttgart and Ulm, southwest of Germany, Baden-Württemberg. So I'm personally working on photovoltaics. I'm head of the division of photovoltaics. I'm also professor at the Karlsruhe Institute of Technology for thin film photovoltaics. So at the ZSW, which is my main job, we are working not only on photovoltaics, we are also working on batteries, on hydrogen, on storage issues, on net integration issues. And in the photovoltaic area, we are focusing on thin film technologies, mainly on CIGS and also on perovskites, but also on system integration, on performance of solar cells, on net integration of PV and so on. So we're covering the full area. So to the tandem cells, I want to say that from my view, this is the only option to boost further efficiencies, because technologies like CIGS, silicon, and others are well above the 20% area. And the tandem technology is one option really to go beyond the Shockley-Queisser limit. And that's why I think that's very important. And it's the only thing, to my knowledge, which is becomes really reality. And yes, the question today, which tandems are most promising, I think this is a very difficult question. I hope we can discuss further aspects of that. So I'm personally working mainly in the past on CIGS. So we have in our lab a CIGS line with cell efficiency well above 22%. We're also making 10 by 10, 30 by 30 modules, and we have a very close industrial cooperation with nice solar in the CIGS field. Thank you.
Maybe, Michael, just to complete, which kind of product are you targeting? Are you targeting the mainstream market? Because we've seen that we have three actually panelists, but they are not really competing. They are proposing different approaches for different markets.
So you mean with the CIGS
yes.
perovskite tandem?
Yes, yes.
So yes, in principle, you can target also the energy market with the thin film CIGS, But yes, you can also target integration market like BIPV and so on. So it's not limited, I think. So the point is, if to bring the efficiency for the modules well above 20%, tandem is a good option, and the all thin film tandem, to my knowledge, is a very good option to bring that efficiency up.
Okay, so excellent. So as you've seen, maybe for the audience, we have 4 panelists, which maybe could all address a different market share, though we don't have to fight tonight. So if I take Thomas, this would be special, maybe lightweight product that you could place everywhere, which is a niche but growing market. Frank would go more for maybe space, satellite, or concentrating application. Chris would extend the learning curve of crystalline silicon, and Michael could also address markets such as structuring the ultra high efficiency tandem cell for making windows that have more than 15% efficiency and lets it 50% of the light through. Is it a good summary?
So Christoph, I'm not limited to this market. We are also doing flexible CIGS and also flexible perovskites. So which could also come to the some kind of niche market. So we at ZSW, we are not limited. We are working for the niche and for the energy market.
Okay.
But okay.
So now you've all shown what you're doing and targeting. Maybe I just would like to continue to review with each of you the challenges that you are actually facing, because we've seen that each technology has its challenges. And I know that you cannot say everything. So I will go with each of you with asking maybe 1 or 2 specific questions where you can then develop on the challenges that you're facing and what you would need to really overcome these challenges. Is it okay for you?
Yes.
If I, for instance, if I come with Thomas, so we have seen the presentation of Michael also McGee yesterday, and well, he showed that you could go for this kind of coupon approach for the perovskite. But he also showed that then you would need likely to have almost 1 bypass diode per cell, or you would need to restrict yourself to places where you have no shading. On the other side, I also checked for the cost of the bypass diode, and I found some for 1 cent, 6 ampere diode. So you could even protect a tandem perovskite cell. So what are the challenges that you're facing in developing this kind of technology, and what would you need to really go faster?
Yeah. First, I wanted to also clarify. I talked about mostly niche markets at first, but we think as a startup, that's the right approach. That doesn't mean that we don't think, you know, in the long run, the all perovskite tandem or the silicon perovskite tandem, all of these tandems are extremely promising for the long term. Just getting the highest efficiency at the lowest cost module in the long term makes sense. So we are looking in that direction as well. In terms of the things that are challenging for us specifically, I'll start with maybe with the bypass diode thing that you just mentioned. Yeah, I think that's coming up as an increasingly important thing to pay attention to, and Mike McGee's done a great job bringing that to everybody's attention, especially because it's just different from what the case in silicon. But like he said, First Solar has similar problems, and they simply don't shade their modules. There are clever ways around these things. There's ways that you could potentially integrate bypass diodes into your module manufacturing process. So it's just a couple simple processing steps. And like you said, bypass diodes aren't necessarily that expensive. And actually the requirements for a bypass diode in a perovskite cell is much different for the bypass diode in a silicon module, where the currents are much higher. And so of course the specs and the actual manufacturers would be different as well for the bypass diodes themselves. Singulating versus monolithic integration is a great question. We can do both. There's nothing that stops you from doing that with the thin film module, from making singulated cells. And again, Mike McGee and Jeremy Werner demonstrated that. In the long term, monolithic integration is the lowest cost option, I think, to my understanding. But there's definitely advantages to having smaller units, like Chris said, like a 6-inch unit. That's easier to scale. That's singulated. You can bin your cells, so you can protect for regions of low yield. And there are also plenty of applications actually where a 6-inch format is very useful. And so we are actually our very first, let's say, mini pilot line that we're that's currently in the works, will be producing smaller, can both produce smaller kind of 6-inch size and then bigger size as well, because there's a need for both.
Okay, excellent. And what do you expect as maybe contribution from the research community that would help you go faster? What do you need to come true here?
Yeah, I think in general with perovskites, the biggest thing that's going to scare anybody away from making a huge purchase of perovskite modules for almost any application is going to be reliability. So the more the research community has standards and understands the fundamental problems, the faster we can all make progress towards that. I think more outdoor testing would be great. There's not much data.
Okay, good. And maybe as Michael is also working on film, I switch to Michael. Here you're trying to combine CIGS, which is wonderful technology, but also not so easy to manufacture, also with some sensitivity to the environmental conditions. So how do you see the advantage also of CIGS versus a bottom cell in perovskite, or are you open to everything? And isn't it combining two different technologies even more challenging?
So you're asking about the challenges. So I think there's one challenge which is which have all technologies together. At the end, we need a square meter module with a 2-terminal. So the module at the end is a 2-terminal thing. So the question is, how do you bring the square millimeters to the square centimeters to the square meter, a tandem module? And from my understanding, for example, and you take a CIGS thin film square meter module, to bring that to a working module for the market in a tandem configuration is very easy if you have the large area deposition technology available for perovskites, which, for my opinion, every technology needs, because otherwise you don't get the low costs. So, for example, if you want to have a large area square meter module out of CIGS, you can easily make the cell width double. You have larger voltage, lower current. So you have no additional, in principle, no additional effort to make to connect the cells to the module. You win a little bit in area because you have less interconnects. But at the end, you can make a module with the same voltage output with a 2-terminal thing very easily. If you because we have a thin film large area technology and we combine 2 large area thin film technologies. I would say this is, for my opinion, the biggest advantage, the best potential for the CIGS combination with perovskites, because then you have thin film on thin film, which is a very homogeneous processing availability. So this is the biggest advantage, I think. But you're asking about the challenges. The challenge is to bring up the perovskites to the square meter level, but this challenge have we all. Second challenge, which is very important, is already addressed, is the question, what is the field experience? How does the perovskite perform in the field? What energy yields do we get? And especially if you combine perovskites with any other materials in a tandem, 2, 3, or 4-terminal tandem, on cell level, the question is, what at the end is the efficiency yield? So this there's no experience from the field today. And I think also you, Christoph, you have experience with tandems in the silicon, amorphous silicon area. But I think this is not comparable, because at the amorphous case, so these spectral effects are not so big in the case of amorphous silicon tandems. But if you have really high fill factors for both cells, so maybe the effect from the field performance is very important, and that's one of the biggest challenge that we can see. What is the, I call that spectral mismatch factor for such a device, in analogous to a thermal factor, loss factor. So this is very important to know. The other thing is costs and so on, but from the technical point of view, it's very important to make a 2-terminal module, large area, how to interconnect. You can make the 4-terminal to or 3-terminal to 2-terminal in the cell area, or you can make it by interconnecting the cells to the module. But at the end, you need a 2-terminal module on a large area scale, which fits to the voltage of the system, which fits to the voltage of the bypass diodes, and which have a performance not losing the efficiency gains in terms of performance. So, and for my feeling, it's if you have a large area deposition possibility for perovskites, which is needed for all, it's very easy to integrate to a large area thin film or thin film tandem with CIGS. Especially for CIGS, other challenges were just discussed also in the talks, but not this view I gave you from the looking on the perspective from the field on the things. If you look on the material science, one thing is clear: it's the growth conditions for the perovskites. But there are options which are very promising in the CIGS field. If you put a little bit of silver in the CIGS, the films are very flat. And this is a very good option to flatten the CIGS and to have better growth conditions for the perovskites, for example. And also we have very good progress in the optics, in the TCO films, and so on. So I'm in good hope that we will soon get very, very good all thin film tandems with CIGS and perovskites, not only in the square centimeter range, also in the square meter range, which is needed, for my opinion.
Okay, we look forward to that. I'll just stay to the perovskite. Chris, here, in principle, you have chosen the easiest approach between brackets. But apparently you have also been delaying the start of, let's say, manufacturing, year after year, and now you announce for next year. So maybe it means you still have some challenges. So we'll be interested to know about your challenges and next steps, and where also maybe you stand today. I know there will be a presentation tomorrow, but maybe you can already give us a
give you a preview. Sure. All right. Thanks, Christo. Well, first of all, I would have to readily admit we're a little bit behind where we thought we would be from a manufacturing standpoint. And I'd have to say it's a combination of the kinds of things you may expect. Impact of COVID, supplier delays, installation delays. We've been able to keep our Brandenburg facility operating, but for a number of months, we could not bring in installation people. So we actually had much of our production equipment arrive in last year and sit in crates for 6 months before the installation teams were allowed to come in, both from their own rules or from the local jurisdiction rules. So that's unfortunate. But we're starting that lineup with the integration of our silicon cell and perovskite top cell together. And again, we chose the 2-terminal approach very specifically because of its elegance and its simplicity, despite the early fears from a lot of people about, current matching and mismatch challenges and spectral response challenges, which in the end have not turned out to be problematic at all. So it's not the kinds of issues we face. We've also found that we are a bit ahead of, I'd say, the commercial industry and some of our requirements. Like if you go out and look at a traditional manufacturing line or module line, they use flash testers to test these products. And we really can't, as a tandem product, be tested with a conventional flash tester. So to get the industry and the people who make these testers to understand those needs, and then perhaps make products for that's important. I mean, we're getting things tested, so we're not worried. Same thing with the side of the industry on the standards and testing. I think just as it took an adaptation of the IEC protocols to be able to test products like CIGS in CAD-TEL, probably some protocol changes need to come into play here, but they're not in particular worries. They're just things people have to catch up with. But in all cases, we try to choose very simple approaches that don't require reinventing, technologies. So the module approach is standard. The stringing approaches are standard. The glass design is standard. The junction boxes are standard, things like that. And it really is because the goal was to get this technology introduced faster. So I have no disagreement with all the other potential applications and approaches for perovskite, including the concepts of all perovskite tandems or triple junctions of two perovskites on silicon, et cetera, in the future. But we'd like to see solar's adoption rate accelerate. And you know what the challenges are. And I think this is the easiest and fastest way to accelerate the adoption of solar is to produce a higher efficiency solar cell. So in terms of what we have is the product is and I'll be very specific here, it's an M6 solar cell. So that's the size. And that alone was a challenge because the solar cells kept changing sizes in the marketplace, so to speak. And of course, it's, when you're not that large, you have to adapt to that. But we've locked on to M6, and there's a reason for it, is the first product is for a rooftop module. And in the rooftop arena, the people who put those up on the roofs don't like to carry things that are too heavy. And there's a practical carrying limit of around 25 kilograms. As it turns out, a 60 cell M6 module weighs just under 25 kilograms. So actually, that's a reason we chose that configuration, to get the most power at a module that could be installed into the initial target market, which is the residential rooftop market. So it's an M6 format solar cell, and it has a full area efficiency of 27%. And trust me, there is no silicon solar cell you can buy today, next year, or ever that's going to be 27% at full area. And that represents our first product. And as we improve the solar cell, we have roadmaps to make that considerably more efficient. So we think it's a very good approach that can adapt to residential, commercial, and then with time, when costs come down, the utility space.
Thank Chris. The case for COVID, of course, is a nightmare when you're installing this line, and it's a very good reason to be delayed. Can you just still mention something about the challenges that are maybe still faced at the, say, manufacturing, or what are the true nightmares?
Well, to a certain extent, we've had to develop a supply chain for these materials, right? I mean, the silicon supply chain is more than readily available, and that's generally out of Asia. But for some of the materials that go into the perovskites, they're readily available, but not in the way you have to have a supply chain nurtured for commercial application. You've got to have multiple suppliers. They have to be ready to ship to a particular quality standard and be able to come. So that's been extra work and challenges for a company that's not very large. I mean, I like to consider us a startup, even though we're not really a startup. I mean, we're 10 years old, but we don't have hundreds and hundreds and thousands of employees. So we have to do a lot of these tasks ourselves. And it is first generation integration. So there's always a bit of learning. And I'd have to say that finally, we do all the normal reliability tests that you would expect and that the industry expects, and field tests, et cetera. But a lot of the additional technical challenge for which we expect the community to help everybody is teasing out the understanding of these materials, so that we have a good view of how they operate. But we're not waiting for the last answer here. We're going to commercialize this product. There'll be things that we learn along the way that will help us improve the product. But it's the same thing that happened in 1954 when the first commercial silicon solar cell came out. It was introduced with only a partial understanding of how it operated. Even it took 5 or 6 more years before the ambipolar diffusion equations, were even published about how those solar cells operated. So, we're going to take all the help we can.
Okay, thank Chris. Now, before we switch to questions, because the questions are starting to pop up in large quantity into the chat. Oh. Sorry, I have. So I have can you still hear me?
Yes.
Sorry, there was a small issue with my computer. Before we switch to the question of the panel, so I asked Frank also the question. So you spoke about the concentrating market, but we've seen that concentration did not succeed in the past in penetrating this market. So one question to you is, do you still see perspective for that? And the second question is, we know that actually the cost of the germanium or even silicon wafer, it might not be the only issue for the cost of the III-V. The III-V in themselves remain very expensive to deposit. So do you see a perspective for this concentration market? And second, do you see any cost perspective for III-V on any kind of substrate? And what are your challenges there?
Yes, of course. I mean, concentrating photovoltaics actually has been very close to meeting the market requirements in terms of cost and reliability. So we did have some years around 2012, 2013, where there were really multi-megawatt installations installed in the world, and they are still running well, some of them are not working well anymore because the companies disappeared and nobody really knows how to maintain them. But in general, I think it has been very close to market. And even if we project energy levelized cost of electricity today, we believe that in the really sunbelt countries of the world, like let's say a country like Namibia or South Africa or the Mexico, Arizona area in the United States, where you see a lot of direct normal irradiation, here really we can meet costs that are on the order of, let's say, a cent per kilowatt hour. But even that, of course, does not differentiate us significantly from silicon, which can meet exactly these costs as well, or even better. And then I think what CPV always has been suffering from is if you're always a little bit too late. I mean, 10 years ago, that would have been fascinating kind of cost target that we could meet, but we're always a little bit behind. And the question is, are we ever gonna make it? Because of course, the number of scientists working on the III-V and CPV is kind of very limited. I just had a CPV conference the last 3 days, and we had like 60 attendees there. And if you see how many people are already here for the tandem workshop, you see that the focus, of course, of the research community is somewhere else. So I think CPV still has one thing that it can sell, and that is it's the highest performance PV technology in the world. So if you're thinking about the amount of kilowatt hours you can generate from a square meter of module area, there's nothing in the world at the moment that can beat these kind of products. And the price is not so much off. So discussing with the community in these conferences today, I think there's lots and lots of good ideas how we can bring the cost down. And you're completely right, the solar cell itself in CPV is not the main cost driver. It's other things like the tracking unit and the module itself and how it is assembled that really adds to the overall cost. But III-V, I think, should not be completely limited to that. So I think the big advantage that III-V can show is that we have a long history going into challenging conditions. I mean, CPV is also challenging because you're dealing with extremely high intensities and temperatures. So these devices really have to be extremely mature to survive these conditions. And the same is true in space, where you have thermal cycling over very high temperature gradients. And so I think the III-V technology has shown that because it's a crystalline technology, it really gives you very high reliability. So the real difficulty in bringing this to more markets, like integrating it into your cell phone or integrating it into, let's say, car roofs and really accessing the high performance that you can get. That, I mean, the best devices we make now, III-V on silicon, are nearly 36% efficient. So I think there is a value in this high performance that we've already discussed also a little bit here in this panel. And the III-Vs can meet it, but the main challenge is the cost. So what do we have to do? If it's not concentration, we have to bring down the cost of the deposition equipment and how to deposit these films, because it's not the gallium and the arsenic that really adds so much to the cost. It's in the end that these reactors are microelectronic machines that are used in industries where you can sometimes get several thousand euros for a 4-inch wafer. So these industries are not so much used to the numbers that we see in the field of silicon photovoltaics these days. And the question is, can we get them there? And that's something we are very heavily working on, trying develop new equipment that can scale, like Michael Powala was saying. I think that's really the key. We need to learn also from the silicon PV technology what we can do to bring down the cost of the 3.5s in the future. And I think there's still lots and lots of ideas, so let's see.
Okay, so thank you, Frank. I don't want to frustrate the audience, and I want just to come to some of the questions of the public. And I'm sorry, I will not be able to address all questions. But there are a few ones that got quite a lot of stand up. And I will start with the question of Marco Yos and the related question of Usama Eraji, who asked about the requirement to enter the market in terms of stability. So we know that the crystalline module are going towards this 30 years warranty for some companies with quite low degradation rate. Do you think that, for instance, a perovskite-based module could already live with a 15 years warranty, or you need to enter with a similar kind of warranty? And I'd be interested to know about that. And an additional question, which is directly for Chris, is if you target a market entrance next year, did you have enough time to really guarantee the stability of the panels, and according to which criteria? So I would let open for who answers. Well, the second question is clearly for Chris, but maybe for the other person, do you have an idea about could you come onto the market with a higher efficiency product with less guarantee than a standard crystalline module?
I'm just going to make a comment. There are going to be market applications for different kinds of products. And I've seen analyses and published papers that there's even potentially a market for a relatively low efficiency product if the cost is low enough, right? Even if its durability is perhaps 10 years. Certainly the application for things like UAVs or drones, where their expected lifetime is maybe 5 years. You don't have to have the same durability as a conventional silicon market. With respect to the product that we've chosen, again, we've chosen something very specific because we're not looking at just smaller market segments or limited durability segments. We're looking at something which can change the world's usage of solar. And that's the utility scale application. So for there, the lifetime has to be 25 years worth of performance and 15 plus years worth of reliability and warranties. And we don't see any evidence from our tests that we're not going to meet that. So we absolutely believe that's what has to be met. And of course, we absolutely hope that we are going to meet them with our product. We don't have more than a year and a half or so of field data, but the field data supports evidentially that we'll have a product that can meet that expectation. But I think there will be a variety of products. There's a company in Europe that's looking at the Internet of Things for their application space. Totally different product class. And obviously, if you were thinking about automobile applications, the automobile devices do not have to last more than 10 years. And that's all the expectation is. So it's different. But for the product in the conventional utility scale, things that look like solar modules, it better be 25 years.
Okay, 25 years is a number to take for today, and you're confident it can be reached with perovskite. Maybe one question to Swift Solar. If you are going for tandem perovskite, you need to introduce tin, and we know that even though results are also improving, stability might even be more of a challenge. Or how do you see the stability, ignoring, let's say, the reverse bias voltage issue? How do you see the stability for lower bandgap perovskite?
Yeah, I currently don't see it as anything that different from the other perovskites in our experience, if you make the right composition and the right structure. But I'd like to also go back to Chris's point that there's applications where lifetime requirements are very different. So that's exactly why we choose this strategy, is that we don't need to warranty 30 years for the applications that we're targeting. We need to guarantee a couple years. And so that's just helpful right now. In terms of stability of the tin perovskites, the best way that we can test these things is to do the standard tandemPV tests, thermal cycling tests, high temperatures unencapsulated. And at the moment, we're passing all of those tests. Just 1,000 hours so far, because these things take a long time, but 1,000 hours damp heat tests with a flexible all perovskite tandem with no degradation that we can see at all. And so far there's no evidence to suggest that normal packaging isn't going to be good enough. Even flexible packaging isn't going to be good enough to meet those kinds of requirements specifically for the low band gap perovskite.
Okay. Does anybody want to add something on the topic?
I'll just note that, again, we also use standard tests, but we've also developed in-house a series of tests that, tease out some of the things that are unique to the perovskite. And they tend to incorporate, let's say, more light and maybe more temperature, but I won't, elaborate beyond that. But for the standard test, even though the certification requirement is IEC, 1X IEC, we're talking specifically about going beyond that. So we're targeting damp heat 2000 and TC 600 or TC 800 because there's evidence that the most reliable products produced by the reference suppliers in the industry have also decided that those are the points at which the highest reliability products meet customer expectations.
Yeah. But maybe here I have really a question that for me is very important. Most of the tests and certification were designed for product whose behavior is known, even for amorphous silicon, where you had this slow degradation, but which is reversible, and that's why you define tests like 1,000-hour light soaking. In of perovskite, in most of the publication, at least, we always see that there is still some degradation occurring after 1,000 hours of illumination. So you can pass 10,000 damp heat hours, but if your modules degrade at 65 degrees and continues to degrade after 1,000 hours, and there is no test that really would address that. So what should be the ideal test so that a product can enter the market? And because this is an important question, how can you give trust to people in such products?
Well, Christoph, it's a great question, but it also sort of validates the approach we're taking for market introduction. So the market of the residential rooftop is not a market like utility. First of all, it's much less sensitive to price because these are people who want the best they can get, the most power they can get, and usually have a limited amount of rooftop space. So they need that higher power product. Second, they're not interested in the levelized cost of energy. So they don't study the energy yield of a product, right? They just want to get that headline power rating for their product. And of course, being less cost sensitive, they'll pay a higher price. And we're expecting that in that application, we'll be able to demonstrate it works well, and performance on the rooftop after a few years will build confidence for the commercial customers and the utility customers into the bankability, so to speak, of the product. So we're going to piggyback on the bankability that we learn from our initial residential customers. Now, that's not a direct answer to your question, but what we look at most importantly is how are our panels degrading outdoors, because we don't have other great tests, and we compare them to standard industry panels. And there, the performance actually looks very, very good. So
I'd love to follow up on this one. I think the point that Christoph brought up on combining some of those stressors that aren't in the standard IEC tests is super important. And I think that's exactly what the academic community should focus on. It's combining those things, doing those tests and understanding why you have to do that test and what the acceleration factor is, rather than doing 10 years of outdoor field testing to know what the answer is. Having an actual accelerated test is going to be arguably one of the most important things in the field, I think.
Absolutely. That's where the community can help.
From our experience in our SOLAB, I can say that every specific photovoltaic materials has its specific aging issues. So we also can expect that for perovskite. So I think it's very important that we develop also accelerating aging methods to see what happens with the perovskites, and in parallel to do the outdoor testing and see what happens in the outdoor. So it's very clear for me that we need specific adapted testing methods and specific adapted accelerating aging methods to test in and to make the norming and everything for the perovskites. And we should not do that too late. We should do that in parallel to the development of the commercial products. That's very important, I think.
Thank you, Michael. Unfortunately, the time flies. It's already 40 minutes we've been discussing, so we are formally at the end of this panel discussion. There are still a lot of questions open. We answered a couple of them already during the discussion. I invite people to contact you directly if they have maybe more specific question, or you can even check the question on the chat. I think we've seen at least we had messages of optimism on what is ongoing in the field of perovskite, different market that you can penetrate for different products, not fighting directly with the cost of silicon. We've also seen that 3.5 could still play a role with a focus on the manufacturing equipment, which, by the way, is certainly a topic I wanted to discuss with all of you about the production technologies for the different products. But unfortunately, the organizers let us only with this miserable 45 minutes to discuss. So with that, I would like to thank all the panelists for taking part and for discussing openly. I hope that the audience enjoyed the discussion, and I would close the panel now and give back the word to Lars Korte. Thank you very much. Bye-bye.
Thank you.